Hi everyone, welcome to the second part of our species richness practical. Let's pick up where we left this last time. In our previous practical, we were looking at how species accumulation curves can help us estimate true species richness, even when we've only conducted incomplete sampling. Now we're going to examine how we can use data from incomplete sampling to more rigorously or objectively estimate total species richness. And then we're going to examine similarity between samples, thinking about how species composition can inform conservation decisions. So just a reminder that we're using data from the Woodbush granite grasslands in Limpopo as our real data here. And of course you guys, for the exercises within this prac, will be using the data set you generated last time, using the sampling of beads from a bag. The Woodbush granite grasslands, remember, are these critically endangered grasslands just to the east of Polokwane. We know from the plots which have been surveyed in those Woodbush granite grasslands that at least 142 species occur in these grasslands. We know that because that's the number that were actually observed. However, we also remember that sampling was incomplete sampling. Therefore, we know that there's a good chance that we haven't recorded all of the species. And indeed, when we look at this species accumulation curve here in blue, we see indeed that not all the plant species have been recorded because that curve hasn't asymptoted. In other words, it hasn't leveled off. When we look at this, the shape of this curve, and estimate at what level it will level off, we could estimate that there's somewhere more than 170 species occurring in these grasslands. Now, the first thing we're going to focus on today is how do we change, or how do we convert your species accumulation curve from the previous prac, which looks something like the curve on the top left, which is jagged. How do we change that to a smooth curve like the blue line on the bottom right? And the answer to that is we will randomize the order of your samples. If we were to have our first sample be a very species-rich sample, our curve would start up high and flatten quickly. If our first sample was a very species-poor sample, our curve would start really low down with low cumulative species richness and would increase far more rapidly. So the order of our samples matters, and the best way around this is to repeat our species accumulation curves for different orders of our samples. So that's what we're going to do. Formally, we would call this a randomized species accumulation curve. However, I'm not going to ask you to perform a lot of randomizations of your curve. I'm only going to ask you to do it 4 times. These are the instructions here, but let me show it to you first in the slides, and then I'll put up these instructions again. So, the way that we would create a randomized curve is we would randomize the order of our sites. So here, this is the dummy data set that we used in the last practical for demonstration. And what you can see there is as you go from the top row to the bottom row, those sites are in the order that we sampled them, A, B, C, D, E. However, we can change the order of that sampling. So for example, we could invert it, that we go in reverse order. Site E on the top, then D, C, B, A. If you look on the right-hand side, what you see there is that we have very different patterns of species accumulation. For the top grid, we see that the cumulative species richness goes from 3 to 4 to 4 to 5 to 6, whereas for the bottom order of sites, the first site has 5 species, and after the second site is added, the curve levels off, right? It stays at 6 species. Both of these matrices have the same total number of species. In fact, both have exactly the same data, but you see the order in which the sites are entered into the species accumulation curve affects the shape. So I'm going to ask you to have 4 randomized orders of sites. You might choose to use the example here and just have one in reverse order. You might then choose for the other 2 to, for example, go site A, C, E, D, B as an example, and then a different order. So this is our original species accumulation curve, and what we will then do is we will plot onto it the species accumulation curves that result from changing the order of the sampling. So here you can see our reverse order. It goes 5 species and then levels off at 6. Here we can add a curve from another order of the sample and another order of the sample and a final order of the samples. What's important to note here is that in all 5 curves, they all end with the number of samples being 5 and the cumulative species richness being 6. If any of your curves end on different points, then something's gone wrong and you need to look at your calculations. Now, the next step here is that we're going to work out the average cumulative species richness curve. Here we've plotted this average cumulative species richness curve in orange, and every point there is simply the average of all the cumulative richness scores for every given number of samples. And what you see here is that this orange curve is much smoother than any of the individual curves that it comprises. However, you'll see it is also still a little bit jagged. It's not perfectly smooth. And if we were to add more randomizations, if we were to maybe have 20 different orders in which the samples were arranged, then we'd end up with a smoother curve still. Okay, these are those instructions. I'd like you to pause this video here to follow those instructions and generate your own randomized curve based on your bead data. Okay, let's move on. So, based on your randomized species accumulation curve, how many species do you think occur in your sample? In other words, how many different types of beads are in that bag? Take a moment to look at your randomized curve, maybe compare it to your original curve from the previous prac, and see how many species you would estimate just visually from that curve occur in your sample. Pause the video here if you need a moment to do this. Okay, so moving on. I think one of the things that's obvious from looking at your species accumulation curve, even the randomized one, is that there can be quite a lot of uncertainty. Your group partner might look at that curve and say, well, they think it levels off at 25 species. You might look at it and say you think it levels off at 20. And what we want to do in the next part of this practical is to think about how we can go from a subjective guess to a more objective estimate of how many species there are in that sample in total, even though you've obviously only sampled incompletely. So let's return to this example of the 2 forest communities. Both have 4 species, but within each community there's very different dominance. Community 2, species A, you can see makes up 80% of the individuals, therefore it's hugely dominant. Where in community 1, all 4 species are equally abundant. We could say they have the same evenness. So let's see if you can get this one right. Which of these 2 forest communities is more species rich? Take a moment and think whether it be community 1, community 2, or whether there's no difference. Hopefully your answer now is there's no difference, because both contain 4 tree species And species richness is just the total number of different species. 4 and 4, therefore no difference. Okay, so let's ask now, which community has higher species diversity? Community 1 or community 2? Well, the answer here would be community 1, because species diversity has two components, species richness and species evenness. And because the richness is the same in both communities, it means that evenness is going to determine which is the more diverse. And since community 1 is higher evenness, it is the more diverse community. Okay. Let's now take this one step further. This is a bit tricky, so think through it carefully and pause if you need to. In our two tree communities, which community do you think we're more likely to find new unrecorded species if we add more samples or if we expand our sampling? Well, the answer here would be community 2. And the reason for this is that generally communities that contain more rare species are thought to be more likely to contain other rare species that have yet to be sampled. We can say this in a different way. Communities that have more singletons, in other words, species that have only been recorded once, so that's just a measure of rare species, that communities with many singletons are likely to have more species that will be discovered or added to our list if we do more sampling. Now this pattern is really important, and it's the basis for a series of methods called species richness estimators. This is a set of mathematical formulas essentially that when you tell it how many species you've observed and you tell it something about how many rare species you have in your community, will give you an estimate, an objective estimate of how many species there really are in the community. Let's now take this and apply it to our wood bush granite grassland data and see how many species there are estimated to be in that community. So on this curve you can see the bottom yellow line, it's marked with an S for species richness. That line shows how as the number of plots increases, so does the number of observed species. And we know that this was 142 species that were observed. But we also know, because that curve hasn't leveled off, there are very likely other unrecorded species. So the 4 curves above it represent 4 species richness estimators that are estimating how many species there truly are in that community based on the characteristics of the data that was collected. It's interesting to note here that the species richness estimators give a wide range of estimates for true species richness, but they do all agree that there are at least 30 odd species that still are likely to be found with more sampling. The next exercise that I would like you to do using your bead dataset is to estimate total species richness using the Chow estimator. This is one of these species richness estimators. To do this, you need to count the number of singletons and doubletons in your site. Now, note this carefully. A singleton is a species that's only been recorded at one site. It doesn't matter how many individuals have been recorded. A species is a singleton only when it's been recorded at just one site. Similarly, a doubleton is not a species where 2 individuals have been recorded. Rather, a doubleton is a species that's only been recorded at 2 sites. Okay, so to apply the Chow formula, what you need is your observed richness. In other words, that's the number of species that you've recorded through the incomplete sampling. And then you add on this term, the number of singletons squared divided by twice the number of doubletons. That will then give you the total estimated species richness. Now, it's important to note, because this will occur in several of your data sets, if there are no singletons and no doubletons, then that second term falls away. And we end up saying, or we end up assuming, that the total estimated species richness is the same as the observed species richness, because there are no rare species, no singletons and no doubletons. Okay, so let me illustrate how this would work before you try it in your own data set. If you look here at our dummy data set again, I'd like you to think about how many singletons and how many doubletons are present in this data set. What you will see is that we have one of each. So remember, a singleton is a species that was only found at one site. Therefore, species 6 fits that criteria. And a doubleton is a species that was only found at 2 sites. So species 5 matches that criteria. Let's then put this into our formula here. So we know that 6 species were observed, because we can see that from the top row of our matrix. We also see there's one doubleton, one singleton. So when we complete that formula, we see that it says the total estimated species richness is 6.5 species. So take a moment and pause the video if you need to. But what does half a species mean in this context? The simple answer here is that half a species doesn't represent an estimate that there's a hybrid or something like that. It merely means that the total estimated species richness is more than 6. Okay, so based on your species richness estimator, how many different types of beads do you think were in your bag? Well, the answer here, the true total richness, would be about 17 species in every bag. It's possible that there are differences in how you classified beads as species, and it's possible that some of the smaller beads have been lost. You should have a number around about 17. Let's move on then to the last idea we want to consider in this practical. We've now used species richness to choose the patch which is the highest conservation priority. But how do we then choose our second highest priority? What criteria do we use for that? Now, of course, we could choose a patch that has the second highest species richness, and that would make sense. We could also choose to use the patch that is closest to our first priority, based on the idea that that would then give us 2 patches that have a good connectivity and maybe even the opportunity to link them through a corridor. The third criteria that one could consider, and this is the one that we're going to explore now, is the idea that we want a patch that has very different species composition. This idea then is called complementarity. It's based on the principle of if we want to have every species protected within a conservation network, when we're adding areas, when we're proclaiming new reserves or targeting areas for conservation, then we need to be selecting areas to target species that aren't already protected in an existing nature reserve. We could say that complementarity then would be the degree to which species which are absent from one area are present in another. In other words, this tells us how big the difference in species composition is between 2 areas. If the species composition is very different, then those 2 areas have high complementarity. This in a way is a way to avoid duplicating which species are protected in our nature reserves. Okay, I think this is a fairly intuitive idea, but let me illustrate it for you guys on the next slide. Okay, so let's imagine that our first priority for conservation is the site shown here in blue. It contains 8 species, with each species indicated by a unique letter. Let's then imagine that we have 3 candidates to be the second patch conserved. If we were just looking at total species richness, then the top patch would be obviously the one that we add to the conservation network because it's got more species than the other 2 patches. However, if we're looking at this from a complementarity perspective, we can see that the second patch has more unsampled or new species than either of the other 2 options. Indeed, all 4 species in that second green patch don't occur in the richest site. Therefore, this second green patch has the highest complementarity. Now, complementarity is an idea that's used in conservation planning. The reason for this, it allows us to be most cost efficient when adding areas to a protected network. We can really target areas that will add as many species as possible to our conservation areas. An example on the bottom of the slide here, that's the distribution of the world's 55 mangrove species. And you can imagine that if we were to conserve the areas with the highest mangrove species richness, we'd be selecting lots of areas around the Philippines and Indonesia. However, if those were the areas that we were conserving, we'd be missing some of the species. However, using the complementarity approach, we can identify just 5 locations across the world that would allow us to conserve all 55 species. Obviously, we want to conserve more and bigger areas, but if we have to just be most cost efficient, you can see that complementarity is a really good way to do that. Those would then be the 5 locations, and only one of them occurs within an area of high richness. Let's look at a different example. This is the nation of Papua New Guinea. The green areas on these maps represent the existing conservation network. Red and blue then represent areas of high and low complementarity respectively. Therefore, if we were investing in new conservation areas in this country, we would want to be targeting the red areas because they represent places which contain species which are not well represented in the existing conservation network. Okay, how do we go about working out this complementarity? Well, again, there's a simple set of mathematical tools to do this, and the one that we're going to focus on here is probably the simplest, and it's the Jaccard index, or the Jaccard similarity coefficient. You see there the formula. It's just the number of species common to both samples divided by the total number of species in both samples. Okay, now that can be a little bit confusing, but I'd like you to have a look at the 2 diagrams below and see if you can work it out. Okay, each symbol there again is representing a different species. Here you can see I've now merged them into a Venn diagram. And what do we have? We've got 2 species that occur in both sites. And when we add up all of the unique species, we see that we have 12 different species in total. As a result, the Jaccard index for this comparison of the 2 sites would be 2 divided by 12. One of the things that's really neat about a similarity index is that it takes compositional data for 2 samples and reduces it to just 1 number. Maybe you're comparing 2 sites, each of which have several hundred species. This index will give you just 1 number that describes how similar those 2 samples are. A value that's close to 0 suggests that the samples are very different. In fact, 0 would say the samples have no shared species, whereas a value of 1 says that you have exactly the same species in both sites. What's worth noting here is this version of the Jacquard index that I'm presenting to you doesn't consider abundance. It only considers the presence of species. So to explain this, think back to our two forest communities that we've used. Both have 4 species, and both have the 4 same species. Therefore, if we're only thinking about the presence of species, their similarity is 1. They are exactly the same. However, if we build into this their abundance and their evenness, then of course they're not exactly the same. Because in community 1, all species are equally abundant. In community 2, there's 1 clearly dominant species. So just bear that in mind, but remember that in most cases we are only working with the presence of species because we don't have good enough data to also work with their abundance or their cover. Here is a real-life example. So this is showing us Site A and Site B, and these are plots surveyed in the Magaliesberg. And I want you to take a second and look at this and think how you would calculate the number of species common to both sites and the total number of species. So pause here and have a look at that. Okay, so to determine the number of species that's common to both sites, on this table that would simply be any species where it was observed in Site A and Site B. So Themida and Panicum, the top 2 rows, you can see those species are recorded both in Site A and Site B. So that represents a species that's common to both sites. When we add that up, we see that there are 7 of them. The total number of species here is then just the total number of rows. So that would be 12, and therefore our Jacquard index is calculated as 7 over 12. What I'd like you to do now as the last exercise in this practical is to estimate the similarity between your richest site and every other site. So in this example we're using Site A as our richest site, and we're then going to calculate the similarity between A and B, A and C, A and D, A and E. So I'd like you to do this for the comparison of your richest site against the other 4 sites. So pause the video here and run those calculations. Okay, so what Jacquard index values did you calculate? Now from previous practicals we've seen broad ranges. But remember, if your values are not between 0 and 1, and they can include 0 and 1, then something's gone wrong and you need to look at your calculations. Equally, you should be able to see, when you look at your data, that samples that have higher Jacquard similarity coefficients should have more similar species composition. In other words, there should be more species in common. Again, if that doesn't look like it's the case, have a look at your calculations again. Okay, so you have now determined the similarity in species composition between your richest site and your 4 other samples. Which sample would you then list as your second priority for conservation? The answer here, of course, would be you want the species with the lowest similarity, because the lowest similarity is the same as the highest complementarity. Okay, I want to wrap up one set of ideas here. In this practical and the previous species richness practical, we've looked actually at 3 measures of diversity, and I want to just explicitly mention those. The first is alpha diversity. That then is the number of species that we've recorded or estimated in just one patch. Second, this is what we've been doing now, we've been thinking about beta diversity. The turnover or the difference in species composition between patches. This beta diversity is the opposite of similarity. Higher beta diversity means bigger differences in species composition between patches. And then at the broadest scale we have gamma diversity, which then is the richness across the whole landscape or across all of these patches. And again, we could estimate this also using species richness estimators. Okay, thanks guys. The last thing for me is just to remind you that you have an assignment based on the second part of the species richness practical. The instructions for this assignment are part of that same instruction file that's on ClickUp. Remember that you're going to continue working with your unique data set that you've already downloaded from ClickUp. So don't use your bead data set here, please. Use the same data set that's unique to you that you used in the first part of the practical. You will also need to remember to download 2 additional data sets from ClickUp. They are stored under the file name extra sites. Thank you and good luck with the assignment.